Next question is, hydrogen atom are excited from the ground state. Ground state refers the first orbit to the principal quantum number 4, and this 4 refers the fourth orbit, that is n2 equal to 4. Here it is n1 is equal to 1. Then the number of the spectral lines observed will be in emission spectrum. In emission spectrum, number of spectral lines will be equal to, and we have to remember this formula, n2 minus n1 into n2 minus n1 plus 1 divided by 2. So if we put the higher energy state, that is n2 4 minus ground state, it is 1, 4 minus 1 plus 1 by 2, so it will be equal to 3 into 4 by 2, and it is equal to 6. So we will have 6 spectral lines. A figure, say this is the n1, n equal to 1, this refers the ground state, and from ground state this electron is first excited to n equal to 4, that is fourth orbit, and from the fourth orbit it returns to the ground state and providing the line spectra, emission spectra. So possible ways of the transitions are from n equal to 4 to n equal to 1 directly. This is one of the spectral lines. Another is n equal to 4 to n equal to 2, and from n equal to 2 to n equal to 1. So in this way it gives two spectral lines. Another way is it may return from n equal to 4 to n equal to 3, and then n equal to 3 to n equal to 1, or from n equal to 3 to n equal to 2, and n equal to 2 equal to n equal to 1 is already included. So in this way we have total 6 spectral lines. This is the answer. So number of the spectral lines in emission spectra will be 6. In the absorption spectrum, electron absorbs the energy and transit to the higher energy state. So in this case, absorption spectrum will have equal to one spectral line, because here electron was initially in ground state, and after receiving the energy it directly reached to the n equal to 4 orbit. So that has only the one spectral lines in the absorption spectrum, and it is to be noted that absorption spectrum involves only the excitation of the ground level to the higher energy level. Therefore, absorption spectrum have the transition from n equal to 1 to 2, or 1 to 3, or 1 to 4, and so on. While in case of emission spectrum, there are the number of spectral lines from higher energy state to the lower energy state. The ionization potential of the hydrogen atom is, it will be 13.6 volt, and in terms of the ionization energy it will be 13.6 electron volt. Hydrogen atom in ground state, that refers n equal to 1, are excited by the monochromatic radiation of photon energy 12.1 electron volt. According to the Bohr theory, the spectral lines emitted by the hydrogen will be, we have to find the number of the spectral lines. We know that ionization energy is 13.6 electron volt. That means if electron is in ground state, so to excite this electron to n equal to infinity, it requires 13.6 electron volt, that is called the ionization energy. So energy of the nth orbit will be minus 13.6 by n square electron volt, which we have already discussed. In ground state, the energy is, if we put the n equal to 1, it will be minus 13.6 electron volt. And electron in ground state, this is the ground state, electron get a photon which has energy equal to 12.1 electron volt. So electron jumps to the higher energy state, and this energy state will have the energy, that is minus 13.6 plus 12.1, that is equal to minus 1.5 electron volt. Now we have to find the number of the orbit for which this energy exists. And as per the formula, energy of a particular orbit is minus 13.6 by n square. So we can write minus 13.6 by n square equal to minus 1.5 electron volt. This implies that n square equal to 13.6 by 1.5 and it is approximately equal to 9. So n equal to 3. Therefore, we can say on receiving the photon of the 12.1 electron volt, this electron which was in ground state will reach in a state of n equal to 3. Therefore, number of the spectral lines in emission spectra, we use formula that is n2 minus n1, n2 minus n1 plus 1 by 2. Higher energy state is 3, lower energy state is 1, so 3 minus 1, then 3 minus 1 plus 1 divided by 2. That is equal to 2 into 3 by 2, 2 get cancelled, so it is equal to 3. Therefore, there will be 3 spectral lines in the emission spectra. If we draw the spectral lines in the diagram, the one of the spectral line may be from n equal to 3 to n equal to 1. Another will be n equal to 3 to n equal to 2 and then n equal to 2 to n equal to 1. So there are the 3 spectral lines in the emission spectra of this atom. Next question is, when the electron does transition from n equal to 4 to n equal to 2, then the emitted line spectrum will be dash line of the dash series. That means which number of the line and what is the name of the series. We know that wavelength of the spectral line in the hydrogen spectrum is given by 1 by lambda equal to r into 1 by nf square minus 1 by ni square per centimeter, where r is the Rydberg constant, ni is the initial energy state that is having the higher energy, and f is the final energy state, and lambda is the wavelength emitted during the transition. We know that for n f equal to 1, we have Lyman series. Similarly, for nf equal to 2, we will have Bohr series. N equal to 3, there will be a Paschen series. N equal to 4 gives the bracket series, and nf equal to 5 gives the Pfund series. So nf equal to 2 gives the Bohr series, and this n equal to 2, this is the final state. So we will have the Bohr series. Now, what is the number of the spectral lines in this series? For n equal to 4, because say this is the n equal to 1, this is 2, this is 3 and 4 and so on. Initially, electron is at n equal to 4 and it transit from n equal to 4 to n equal to 2. So, first series of the Bohr is given by the transition from n equal to 3 to n equal to 1. This is the first spectral lines in the Bohr series, and then second will be n equal to 4 to n equal to 2. Therefore, the spectral line of this transition will be the second line of Bohr series. This is the answer. Next question is, consider the spectral lines resulting from the transition from n equal to 2 to n equal to 1 in hydrogen atom and single electron ions. The shortest wavelength is produced by, there are the 4 options: hydrogen, deuterium, helium and lithium. We know atomic number of hydrogen is 1, for deuterium is also 1, helium it is 2 and lithium it is 4. And already we have derived the formula for the wavelength, that is 1 by lambda equal to rz square if it is for the hydrogen or hydrogen like atoms, and 1 by nf square minus 1 by ni square, where z is the atomic number of atom. Here nf and ni are same in all the 4 hydrogen, deuterium, helium and lithium ions. So this parameter is same and Rydberg constant is already same. Therefore, we can write that lambda is inversely proportional to 1 by z square. For shortest wavelength, if this is to be shortest, then Z should be maximum. So this concludes that lithium ion will have the shortest wavelength. So this is the answer. Ground state energy of hydrogen atom is minus 13.6 electron volt. Ground state refers the n equal to 1 orbit, and energy of nth orbit is given by minus 13.6 by n square electron volt. Therefore, for ground state n equal to 1, this refers the ground state. This implies that E1 is equal to minus 13.6 by 1 square, that is equal to minus 13.6 electron volt. This is given in the question. The energy needed to ionize hydrogen atom from its second excited state. First excited state refers n equal to 2, and second excited state refers n equal to 3. So energy of the third orbit will be equal to minus 13.6 divided by 3 square electron volt, that is equal to minus 13.6 by 9, and it is equal to minus 1.51 electron volt. So as per the question, electron is in second excited state, and from the second excited state it is ionized. Therefore, to ionize, the final energy state will be infinity, and that has the energy 0. Therefore, ionization energy from the second excited state will be equal to the E infinity minus E3, that is equal to 0 minus 1.51, that is equal to 1.51 electron volt. The ratio of the longest wavelength corresponding to the Lyman and the Bohr series in the hydrogen spectrum is, we know that wavelength has the relation 1 by lambda equal to R into 1 NF final energy state minus 1 by Ni square initial energy state. For Lyman series, we know that NF is equal to 1, and for Bohr series NF equal to 2. So we can write 1 by lambda is equal to R into 1 by 1 square minus 1 by N square. Similarly, for wavelength of, this is the Lyman series, this is the Bohr series, R into 1 by 2 square minus 1 by N square. For shortest wavelength, the orbits involved in transition must be nearest. That means for Lyman series, if we have to find the shortest wavelength, then this n should be nearest to 1. That means this n should be 2. Similarly, if in case of Bohr series we check the final energy state is 2, so initial energy state should be nearest to 2, that is it is the 3. So n equal to 3 will give the shortest wavelength for the Bohr series. Therefore, we can write 1 by lambda L, that is equal to 1 R into 1 minus 1 by 4, that is equal to 3 by 4 into R. Similarly, for Lyman series, Bohr series, we can write 1 by lambda B, that is equal to R into 1 by 4 minus 1 by 9, and it is equal to R into 5 by 36. Now we have to take the ratio of Lyman and Bohr series, so lambda L by lambda B. For this, we have to divide this expression 2 by 1. If we divide expression 2 by 1, we will have 5R by 36 into divided by, and this is 3R by 4. So this implies that 5R by 36 into 4 by 3R, is R and R get cancelled, 4 get cancelled 9. So we will have answer 5 by 27. This is the answer. Given the value of Rydberg constant 10 raised to power 7 per meter, R is given 10 raised to power 7 per meter. The wave number, and wave number is, we have already defined that 1 by lambda is known as the wave number of the last line of Balmer series. Balmer series refers that NF is equal to 2, final energy state will be 2, and the initial will be, for last line, it is infinity. In hydrogen atom will be, so using the formula 1 by lambda for hydrogen atom, it is R 1 by NF square minus 1 by N1 square. This implies that 1 by lambda, that is equal to wave number, it is equal to R into 1 by NF square minus 1 by N is I square, and substituting the value R is 10 to the power 7 into 1 by final energy state is 2, so it is 2 square minus 1 by infinity square. 1 by infinity is 0, so it gives 1 by 4 into 10 to the power 7, or we can write nu bar equal to 0.25 into 10 raised to the power 7 meter. This is the answer.